Hi everyone. So in this video, we're going to be learning about a couple of simple applications of measuring angles in radians. So what we'll see is that there are a couple of very simple formulas that we can use to find the length and area of certain portions of a circle. And basically, if we measure angles in radians, these formulas work out to be really nice. And so while the stuff in this video is not super important, I'd say, compared to other videos, we're not going to really be coming back to these ideas too much throughout the quarter. It's kind of like a one-off video, but I hope that this video kind of helps you see why radians are a good way of measuring angles. So, I know that at least at the beginning of the class, radians just feel very tricky. They feel much less natural than degrees. But what we'll see is that they actually are more natural in a lot of ways, especially when you're talking about angles as they relate to circles. Okay, so what am I talking about when I say an arc or a sector? So arcs and sectors, they're basically just different portions of a circle. And so if you take a circle and you kind of imagine cutting a slice out of it, like as if it was like a cake or a pie or a pizza, something like that. So I'm going to just kind of cut out a slice of this circle. If you look at the kind of edge of that slice, so basically talking about kind of a portion of the circumference of the circle, that portion of the circumference of the circle, that is referred to as an arc. So we'll see that there will be a formula for finding the length of that arc. And then similarly, if you look at the area that I'm shading in here, so this is now not a portion of the circumference, but a portion of the area of the circle. This is called a sector. And so in order to kind of quantify what portion of the circle we're looking at, right, we could have made this much smaller or really big. Any kind of portion of the circle that is measured from the center and is kind of just a slice of the circle counts as a sector and an arc. And the way that we're going to quantify how big the sector and the arc is by looking at the angle here. So I'm going to label this as theta, but this angle is referred to as the central angle of the arc or the sector. And if you think about it, the central angle really does kind of control what portion of the circle we're looking at, right? The smaller that angle, the smaller the slice. The bigger the angle, the bigger the slice. So the central angle we'll see is really what's going to help us determine what the length of the arc is and what the area of the sector is. Okay, so let's start with an example. So we're going to do an example that kind of, I think will help us get a little bit of intuition about what we're working with here. I'm just going to scooch this up a little bit. And then once we kind of have that intuition, we're going to come up with some actual formulas that you'll be able to use moving forward. Okay, so let's say that we have this circle. The circle has a radius of 3 centimeters, and we're looking at a sector and an arc that have a central angle of pi over 2. So remember, pi over 2 is 90 degrees. It's a right angle. So how can we go about, with the information that is given and without knowing, any formulas, how can we kind of go about finding the arc length and the sector area? Well, basically, by looking at the central angle, we can tell that this sector, we can determine what portion of the circle this sector and the arc are. So maybe pause the video for a second and just, verify for yourself what fraction of the circle are we looking at, and try to do it not just by, eyeballing it, but by actually looking at the angle and kind of figuring out how can you use that angle to figure out what portion of the circle we're looking at. So we're looking at 1/4 of the circle, right? And so, that's visually pretty clear, but one thing with geometry to keep in mind is that you generally don't want to, with geometry, just kind of make assumptions based on what a picture looks like, right? You really want to use the information that's given. And so to be a little bit more concrete about it, pi over 2 is 1/4 of the total amount of angle within the circle. So what I mean by that is if you were to go all the way around in a full circle, what would that angle be? Well, it would be 360 degrees, right? And so 360 degrees in radians, that is 2 pi. And so if you were to kind of compare pi over 2 to 2 pi, pi over 2 is 1/4 of 2 pi, right? If you do 2 pi over 4, that's pi over 2. So pi over 2 is 1/4 of 2 pi. And maybe thinking about it in degrees for a moment makes it even clearer, right? The total number of degrees in a full rotation would be 360. Pi over 2 is 90. 90 is 1/4 of 360. Cool. So now that we know that we're looking at 1/4 of a circle, so let me write that down here. So the arc and sector are basically 1/4 of the circle, right? They're making up 1/4 of the circle. And so how can we use that to figure out, let's start with the arc length. So if we're looking at a kind of portion of 1/4 of the circle, how would we use that to figure out the length of the arc? Well, the length of the arc should be 1/4 of the circumference, right? So the arc length is 1/4 of the circumference. Because arc length, we're talking about a length, right? And so that's kind of the outside of the circle. That makes sense with circumference. And so how could we calculate that? Well, we can just do 1/4 times the circumference of the circle, which we know is 2 pi times the radius. And so in this case, that's going to be 2 pi times 3. So this is going to be equal to 6 pi over 4. And that simplifies to 3 pi over 2. And then what are our units? Well, our units are centimeters, right? So we're talking about a length, so they shouldn't be centimeters squared. They should just be regular centimeters. And that is our arc length. So one thing I just want to point out, because I think it can feel a little confusing in this class, we get really used to seeing things like 3 pi over 2 and thinking of it as an angle. In this case, it's not referring to an angle, it's referring to a length. And you can kind of see that with the fact that we're labeling it with centimeters. So even though for the most part in this class, when we're talking about pi and 3 pi over 2, 2 pi over 3, things like that, usually we're talking about angles. Pi is still a number. Pi can still be used to describe things like the area or the circumference of a circle, or a arc length or sector area. Okay, so similarly, how do we find the sector area? Well, that's going to be now 1/4 of the area of the circle. And actually, let me move this down. I think I'm going to be a little too close here. So the sector area is 1/4 of the circle area. And so that would be 1/4 times, so remember the area of a circle, that's pi times the radius squared. So in this case, that would be pi times 3 squared. And so that's going to end up being 9 pi over 4. And then what are our units this time? Well, this time it's square centimeters, right? Because we're talking about an area. And so area is measured in square units. And just to kind of point this out, this is something I mentioned in our geometry review video. So, this is a circumference formula and this is an area formula, right? And so circumference just has the radius, area has radius squared. And so that corresponds to our units, because if you were to have written the units kind of in this calculation process, this would just be 3 centimeters. This would be 3 centimeters all squared. And so the centimeters end up getting squared too, which is why you end up with square centimeters in your final answer. So just to kind of help you remember the difference between area and circumference. Okay, so let's try to now take this kind of reasoning and we're going to use it to come up with a formula that will work in general for calculating arc length and sector area. So really what we did here is we compared the central angle to the total number of radians in the circle, right? We compared pi over 2 to 2 pi and said, okay, it's 1/4. And so how can we kind of formalize that? Well, really what we were doing is we're kind of making a ratio, right? We're thinking about the central angle compared to 2 pi, right? Because 2 pi is the total amount of rotation in a full circle. And so by taking the central angle and comparing it to 2 pi, that establishes whether you're talking about 1/4 of the circle, 1/6 of the circle, whatever that fraction is. And so if you then take that ratio and set it equal to the arc length over the circumference, you should get that same ratio, right? Because we're saying like it's always the same portion of the circle. So if it's 1/4 of the angle, it's going to be 1/4 of the circumference. So let's take this now and kind of fill it with some different symbols that we've been using throughout this problem, and then we'll basically solve this ratio for arc length, and that will give us the formula for arc length. And we'll see that it comes out to be a very, very simple formula. Okay, so we've been using theta to represent the central angle, right? So I'm going to rewrite this as theta over 2 pi is equal to, and then I'm still just going to write arc length here. And then the circumference, well, we know that that is 2 pi times the radius, right? That's how you calculate arc length. So from here, we want to solve this for arc length, right? Because that would give us our formula for how to calculate arc length. And so if we just take this equation and we multiply both sides by 2 pi times the radius, that will leave us with just arc length in the numerator on the right-hand side, right? So let's multiply both sides by 2 pi times the radius. So that's going to give us 2 pi times the radius times theta over 2 pi is equal to arc length. And so what happens now is that some things cancel out, right? The 2 pi's cancel out with each other. And what we're left with here is that the arc length, just trying to pick out a different color here. I guess I'll stick with this. Arc length is just equal to the radius times the central angle. That is our formula. So just to be clear, the stuff I wrote above, you can always go back to that if you forget this formula, but now that we've derived the formula, we can just run with it. And we'll do a couple examples using it in a moment. Okay, so let's now look at a sector area. So it's going to be the exact same idea, right? Except for that this time, instead of talking about a length, we're talking about an area. So again, we're trying to think about, well, if we can compare the central angle to 2 pi, that's going to give us, determine what fraction of the circle we're looking at. But then this time we want to be comparing the sector area to the circle area. And whatever that ratio is, it should be the same as the central angle compared to 2 pi. So again, I'm just going to kind of clean this up a little bit. Let's write this as theta over 2 pi is equal to sector area divided by, so the area of a circle is pi r squared. So just like we did on the other one, if we're trying to isolate the sector area, we want to multiply both sides by the denominator of the right-hand side. So we're going to end up with pi r squared times theta over 2 pi is equal to the sector area. So again, things are going to cancel out. It's not quite as clean as the last one, but we see that the pi's cancel out. And so what we're left with is that the formula for sector area is equal to 1/2, right? Because we have theta over 2. We can rewrite that as 1/2 times r squared times theta. Or you could write it, if you wanted to, as r squared theta over 2. So the reason that these formulas are so nice and kind of simple is because we're measuring angles in radians. So if you wanted to do this same idea with degrees, you totally could, but instead you would have to write 360 degrees here and here, right? And so what would happen is that the pi's there would be no pi to cancel out. So that's kind of why radians are a very natural choice when you're talking about angles, because angles really have to do with rotation, and rotations are related to circles. So basically by using radians, you're able to take advantage of the fact that both the angle and the circumference, or both the angle and the area, contain a pi, and they cancel out to give us this nice, simple formula. So if you wanted to do it with degrees, basically, I wouldn't try to think of it as a formula. With degrees, I would just kind of start here and write 360 as the denominator. But for the sake of this video and the homework, we're just going to be doing examples in radians. Okay, so now that we have our formulas, we can go ahead and do an example. So this one is saying, find the length of the arc and the area of the sector that have a central angle of 2 pi over 3 in a circle of radius 5 centimeters. So with our formulas in hand, this is pretty straightforward. So to find the arc length, all we have to do is do the radius times the central angle, right? That's our formula for arc length. So r times theta, which in this case is going to be, our central angle is 2 pi over 3. Actually, let me write it the other way. The radius is 5. The central angle is 2 pi over 3. And so our answer is 10 pi over 3. And our units are centimeters. And we're not squaring them because we're dealing with a length, not an area. So that is our arc length. And then similarly, sector area, we just apply that second formula. Oops, I just wrote, sometimes I do that. I say a word out loud and I want to write it down. Sector area. So the sector area is 1/2 times the radius squared times theta. So in this case, that's going to be 1/2 times, so the radius squared, that's going to be 5 squared. And then theta, our central angle, is 2 pi over 3. And so let's clean this up a little bit. That's going to be 1/2 times 25 times 2 pi over 3. And you could just multiply these together, but if you look at what's going on with this multiplication, you'll see that we have a factor of 2 in the numerator and the denominator, so you can always cancel that out before multiplying, just to kind of avoid having to do simplification after multiplying. And so that's going to leave us with 25 pi over 3. And this time our units are square centimeters because we're measuring an area. Okay, last problem. So this is going to kind of be working backwards. So this says, suppose that an arc that is part of a circle of radius 4 feet has a length of 7 pi over 3 feet. And we need to find the central angle of that arc. So this problem in some ways might feel a little trickier, but it's actually just using our exact same formula. So that arc length formula, arc length is equal to r times theta. The only difference is that this time, instead of finding the arc length, we're going to be using this formula to find the central angle. So arc length we know is equal to the radius times the central angle. And so now we can fill in what we know, right? We know that the arc length is 7 pi over 3. We know that the radius is 4. And then we don't know what theta is. That's what we're trying to solve for. But now that we have everything else filled out, we can just solve for theta. So we can do that by multiplying both sides by 1/4. So we have 1/4 times 7 pi over 3 is equal to theta. And so if we multiply these together, we end up with theta is equal to 7 pi over 12. And so that would be the measurement in radians of our central angle. All right, that is it for this video. So like I said, just these two kind of simple formulas. Please check out the worksheet for today. I put a kind of bonus question that I think is kind of interesting so you can see where these kinds of shapes might come up in the real world, and I would encourage you to give that problem a try. All right, I'll see you all in the next video.